Okay, we're now on to section 5 of the proof and mathematical communication chapter, which is now looking at proof by exhaustion. So it's the final part on proof. We've already looked at disproof by counterexample, proof by deduction, and we're now on to this thing called proof by exhaustion. So what is proof by exhaustion? So it is where you try all possible variations, so you're exhausting all of the possible variations in order to prove that something is true. Okay, and maybe you're thinking, well, if you want to prove something is true by going through all of the possible variations there are, you could be there for a very long time, and you're absolutely correct. And this is one of the major disadvantages of proof by exhaustion, and it's not always going to be appropriate. So for example, if we look at proving by exhaustion to prove that there are infinitely many primes, okay, it's not a great idea. You're going to be there all day, you're going to be there for your whole life, because to prove there are infinitely many primes, you literally sat there writing, your prime numbers 2, 3, 5, 7, 11, 13, 17, up into the millions. So clearly, right, proof by exhaustion isn't always going to cut the mustard, but it can be very useful, and it is a nice tool in some cases. So let's look at this conjecture, okay? And a conjecture just means a statement that we believe to be true, which needs to be proved. So the statement here is to prove by exhaustion that 97 is a prime number. Okay, maybe you're thinking, well, to prove that that's a prime number, okay, you could be there for a long time because 97 is quite big. You can be a bit crafty about this, as you're going to see now. But first of all, right, to prove that 97 is a prime number, we must show that 97 has exactly two factors, the number 1 and itself, because this is the definition of a prime number. Two factors, 1 and itself. In other words, there can be no other integer that divides into 97 apart from the number 1 and 97. So maybe you're thinking, okay, let's just work through by dividing through by our integers, starting from 2, 3, 4, 5, up to 97, okay? But again, this might take a long time, so we can be crafty about this, as you're going to see now. But anyway, we can begin by dividing by 2, and if we get a decimal, which we do here, well, 2 cannot be a factor of 97. Okay, so because 2 gives us a decimal answer, 2 is not a factor. So, okay, that's one variation. We can then go on to our next integer, which is to divide 3 by 3. If you divide 3 by 3, okay, you get another decimal, which is good. So therefore 3 is not a factor of 97. Okay, but then do you need to go and divide through by the number 4? Well, you don't, because if 2 gave you a decimal answer, if you divide 97 by the number 4, okay, because 4 is a multiple of 2, you're also going to get a decimal answer. So you don't need to divide through by 4 because 2 didn't work and 4 is a multiple of the number 2. So you can then go on to your next number, which is to divide through by the number 5. And again, if you divide through by your number 5, you get a decimal answer again, which therefore means that 5 isn't a factor of 97. Okay, so we've proved another variation there. Again, do you need to go and divide through by 6 now? You don't, because if 2 didn't work, you had a decimal, because 6 is a multiple of 2. If you divide through by 6, you're going to get a decimal answer as well. So then you might go on to the number 7. Okay, if you divide through by the number 7, again, we get a decimal answer, which means that 7 is not a factor of 97. Okay, so I've been through 4 variations there, but when do I stop? Because I could keep going up. Again, do I need to go and use the numbers 8 and 9? Well, I don't, because 8 is a multiple of 2, 9 is a multiple of 3, and if 3 didn't work, 9's not going to work. So I could then go on to 11, so on, so forth. Okay, when do I stop? That is the question. You're going to see in a second. Note, just before we do look at that in a second, right, these numbers here, dividing by 2, 3, 5, and 7, these are all prime numbers. And the reason that is the case, okay, is that since you can write any number as a product of its prime factors, you only need to check whether it has prime factors. So that's like another way of looking at it, right? Okay, so that is just to note. Okay, so right, we've got up to the point here where we've tried dividing by 2, 3, 5, and 7, and none of these variations have worked, okay? But do we need to go any further to prove that 97 is a prime number? And the answer is, oh, if I can move my pen thing out of the way, the answer is no. Because if we think about what is the square root of 97, okay, the answer is just going to be below 10, because 10 squared is equal to 100, root 97 is going to be 9 point something. This is really, really important. If we were to find any factor above 10, there must have been a factor below 10, so that when the numbers are multiplied, they made 97. So this bit is key. There must have been a factor below 10 so that when the numbers were multiplied, okay, they made 97. And because there is not a factor below 10, 2, 3, 5, 7, these are not factors of 97, okay, then that must mean that 97 is a prime number. And to write that kind of more clearly, we can say, using good mathematical communication, we can say, so, as there are no factors less than the square root of 97, okay, we went through all of the outcomes here, okay, 2, 3, we didn't use 4, as we discussed, 5, we didn't use 6, 7, 8, 9, okay, that implies that there are no factors bigger than the square root of 97. Therefore, 97 is a prime number. So actually, right, we've gone through all of the possible variations here to prove that 97 is a prime number, but we've been crafty about it. Okay, I haven't just sat there mindlessly going through all of my numbers because I don't need to. I don't need to because of this statement here. If there's to find any factor above 10, there must have been a factor below 10. That's really, really important. So we can use that key bit of knowledge there to stop at the number 7. Okay, brilliant. So that's one example of using proof by exhaustion. Let's look at a couple more. So this one is a nice one, which is to prove by exhaustion that no square number ends in the number 7. So just to think about what this question is saying, it's saying if you take a number and you square it, it won't end in a 7. So for example, if you go and take the number 3 and you square it, or 3 squared is equal to 9, it doesn't end in a 7. So that's good. But proof by exhaustion, you've got to go through all of the possible different variations. So maybe you're thinking, well, that's impossible because you'd have to go through all of the examples. You don't, okay? If we go and think about, right, what can all of our numbers possibly end with, right? Any number can be ending with a 0, it can end with a 1, it can end with a 2, it could end with any number up to the number 9. Okay, so let's go and do this. Sorry, my pen pad thing keeps getting in the way. So 7, 8, and 9. So any possible number you can possibly think of, any integer, must end with either a 0 all the way up to a 9. And if you think about, well, if you take a number, for example, that ends with the number 6, for example, like if you went and took the number 26 and you squared it, okay, what is that number going to end with? So 26 squared is equal to whatever it's equal to, but what it ends with is your last number, which is 6. And if you square it, right, you get 36. So this number is going to end with a 6. Okay, so whatever your number is, it must end with a 6. Okay, if you go and square 26, you do in fact get 676. Okay, so you can see, because your last number is a 6, if you square 6, you get 36. Right, your last number there is a 6, so it ends in a 6. Similarly, if you took a number ending with an 8, okay, like you took the number 128 and you squared it, okay, what if you go and take the last number 8 and you square 8, you get 64. The last number there is a 4, therefore this number, okay, must end in a 4. And let's check that. If we go and square 128, hopefully it ends with a 4. It does. 128, and we square it, you get 16,384. Okay, if we take a number that ends in a 3, for example, like 1003, and we square it, because if you square the number 3, 3 squared is 9, your number must end with a 9. Okay, 1003 squared is whatever it's equal to, but I can assure you it does end with a 9. So we can then go through these here and just say, well, if you square 0, okay, a number ending with a 0, like 0 or 10 or 20, your number is going to end with a 0. If you square a number ending with a 1, your number is going to end with a 1. Like 21 squared, for example, is equal to 441. Okay, if you go and square the number 2, 2 squared is 4, your number is going to end with a 4. You go and square your number 3, okay, your number is going to end with a 9. 4 squared, okay, it's going to end with a 6, because 16. If you go and square 5, 5 squared is going to end with a 5. If you go and square 6, it's going to end with a 6. Square 7, 7 squared is 49, it's going to end with a 9. 8 squared, end with a 64, so end with a 4. 9 squared is 81, it's going to end with a 1. Okay, brilliant. So you can see here, right, do any of these numbers end in a 7? Well, 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. Okay, none of these numbers end with a 7. And because all numbers that you can possibly think of must end with numbers going from 0 to 9, there is no square number that ends in a 7. And I've proved it by going through all of the possible outcomes, variations. Okay, brilliant. Let's now look at the question in the textbook, which is worked example 1.10, which is saying a whole number is squared and then divided by 3. Prove that the remainder can only be 0 or 1. Right, let's just go and consider this first statement. So you've got a whole number, it is squared and is divided by number 3. Prove that the remainder can only be 0 or the number 1. Right, if we think about dividing by the number 3, there are 3 outcomes that you could get. If you divide by 3, you could get a remainder of 0, and that would be the case if you have a number which is a multiple of 3. So if we go and say that n is equal to our whole number, okay, just making sure we're defining things nicely. Okay, one variation if you divide by 3 is to have no remainder. Okay, I'm going to write that something like this. We could go and say that n would be equal to 3k, okay, where k is just an integer, so that's just your 3 times table, 3, 6, 9, 12. Okay, if you divide 3 by 3 here, you get a remainder of 0. For example, 12 divided by 3 is 0. A second variation, okay, is you could have a number 1 bigger than a multiple of 3, where if you divide by the number 3, you have a remainder of 1. So for example, we saw previously with this one here, okay, that if you had like the number 12, for example, and you divide it by 3, you get a remainder of 0. If you have a number 1 bigger than 12, like 13, and you divide by 3, you get 4, remainder 1. It's a second variation that you can get. What I'm trying to do here is cover all of my possible numbers algebraically, because I don't want to be going through all of them. That would be crazy. And we can write this time as n being equal to 3k plus 1. Right, and the final sort of number that we could have here is if you divide a number by 3, you have a remainder of 2. So like we took the number 14, you divide it by 3, where you get 3, 6, 9, 12, you get 4, remainder 2. So we could have the number being a multiple of 3, okay, but then plus 2. So that's kind of showing 14 in this case. And the 13, 3k plus 1. And of course, if you went back to 12, 13, 14, you went up to 15. Well, 15 divided by 3, again, would give you a remainder of 0. And then this cycle just repeats. So what I've done here is, right, because to prove this, right, again, it would be crazy to go through all of your possible numbers. Okay, you would be there for your whole life. So I've got to find a way of writing or getting all of the possible outcomes. So if you divide a number by 3, okay, you can cover all of your possible numbers that there are by writing them as 3k, 3k plus 1, and 3k plus 2. Okay, hopefully that made sense. I then want to prove that if I square this number and divide it by 3, the remainder can only be 0 or 1. Okay, so let's go and now do this. So if we go and consider, let's go and break this up into cases. Let's go and call this case 1. Let's go and call that case 2. Let's go and call that case 3. Okay, with case 1, if I go and square this number, so if I go and take, well, n squared, okay, that's going to be equal to, I'm going to be squaring that 3k, so it's going to be equal to 3k squared, and 3k squared I can write as 9k squared. Okay, excellent. And if I want to, right, I could write this 9k squared just a little bit differently. I could write it as 3 bracket 3k squared. Okay, where this 3k squared is just going to be some integer, okay, because k is an integer, so it's just going to be some whole number. This is just going to be your 3 times table again. Okay, so I can write this a little bit differently. I can write this bit here, this 3k squared, in terms of another letter. That's going to write it as m, okay? It's just to make things a little bit clearer. Okay, m is just going to be some whole number. So this I can go and write being equal to 3m, right, which is just your 3 times table, okay? And if that's your 3 times table, if I divide by the number 3, okay, well, the remainder is going to be 0 because it's the 3 times table. So you can see here the remainder, okay, the remainder is going to be equal to 0, which is good so far because it's saying the remainder should only be 0 or 1. Okay, good. Let's now go consider the second variation, which was if your number was 1 bigger than a multiple of 3, like number 13, and if you square this, what's going to happen? So let's go and take a look. So case 2, if I go and take this time n squared, where I've got 3k plus 1 squared. Okay, well, if I square this bracket, squaring the bracket, we're going to be getting 9k squared, 3k plus 3k plus 6k, 1 times 1 is going to be plus 1. Okay, and how can I write this a little bit more craftily? Well, what I could go and do here is I could go and factorize out a 3 and write this as 3 bracket and then 3k squared, okay, plus 2k. Okay, close that bracket. So what I've done is I factorized this part here to give me this part. Okay, they mean exactly the same thing. And I've got that plus 1 still on the end. And again, right, this part here, right, this 3k squared plus 2k, that's just going to be some integer, some whole number, which I can just going to go and replace again using the letter m. Okay, so I can go and write this now as 3m plus 1. Right, and now if I go and divide this, 3m is your 3 times table plus the number 1. If I divide this by the number 3, right, your remainder is going to be 1 because the 3's would cancel out and you'd have 1 as your remainder. So you can see here that your remainder, okay, your remainder is going to be 1 in this case. So we can see good so far, remainder of 0, remainder of 1, we're looking pretty good. For my third case, okay, same thing again, if I go and square my number, so 3k plus 2, okay, so let's go and do that. So if I go and take my number squared, and it's going to be 3k plus 2 now. If I go and square this bracket, we're going to be getting 9k squared, 3k times 2 is 6k, doubling it, plus 12k, and then we've got a plus 4, okay. And then we could write this a bit more craftily by saying we've got 9k squared plus 12k, and then 4 I'm going to be writing as plus 3 plus 1, because then what I can go and do is factorize out a 3 from here and say I've got 3 bracket 3k squared plus 4k plus 1, okay, and plus this 1 on the end, which is it. Excellent. And again, this bit here, okay, it's just going to be some integer. Where k is an integer, that's just some whole number. You're just timesing 3 by some number, which I'm going to go and represent by m. So I can write this now as being 3m plus 1. You can see again, that's the same things as I've got up here. If I divide 3m plus 1 by the number 3, okay, I will get a remainder of 1 again. So there we go, I get a remainder of 1. So you can see, I've run out of room a little bit. If I move my page a bit, there we go. You can see, right, if I square my whole number and divide it by 3, the remainder is either 0 or 1. So we get either a remainder of 0, we get a remainder of 1. And I've proven that for all possible outcomes. I haven't literally gone through all of my numbers, 12, 13, 14, 15, 16, 17, 18. I would be there forever. But I've represented all of my numbers using this up here, because this represents all of the different outcomes you can get if you divide by number 3. Okay, that is it for proof by exhaustion. We'll get on to the worked examples on the next video. Thank you.